I received a question about how to physically make NPT threads in Alibre. So let's cover how to make this, how to make it equation driven. Let's also cover to where I only need to make a few different inputs, right? I just type a few measurements and then it generates the thread for me, and I can use this as a little template to make whatever NPT thread that I want. Let's also cover how to instantly make it the other side, an internal or external thread. We'll be working in nominal today. Nominal should be okay for 3D printing because 3D printing is pretty forgiving when it comes to things like this. And when we make nominal, it makes these kinds of changes very, very easy. And making nominal instead of production NPT threads makes it a magnitude simpler as well. So we'll cover all these things. Now, Alibre, of course, is able to pull up the hole tool. I can select something, and I can choose maybe a threaded thing. We'll go with ISO fine. Maybe we'll go a bit larger, and I can just check the box for modeled, and in somewhat instant fashion, it is able to model that thread for me physically. Likewise, I can choose what condition I want to have that model be. So right now we're looking at a nominal thread, which is what we're going to make today. But I also have the options to do like a max material condition thread, a min material or average condition, which again is a production level thread. So we can produce physically modeled threads in Alibre pretty quickly and easily. The problem is NPT threads have a taper on them, and so they are supported with a cosmetic thread, right? They're not supported with this physical thread. So if I change this to NPT, then it becomes a cosmetic thread. Now you put this in a drawing, you get your thread callouts automatically in Pro and Expert. It's just very straightforward and easy. Just the physical stuff, if you want to do something like 3D print it, is where it becomes an issue. So if we want to physically make this thing, let's take a look at one good tool. Right here I am on Engineer's Edge, and it has a nice, if I open that up a little bit, a nice little threaded chart for us. So we have NPT threads and their dimensions. It's just at this URL, and we can use these dimensions to create our fully defined nominal thread. Let's start a new part and get started. From here, I'm going to create a sketch. I'll hit Control-Shift-P to show my planes. I'm going to sketch on my XY plane. Now in the sketch environment, I'm going to sketch out a taper there. So sketching out this shape, we can start adding dimensions. Now the first thing is, what size do I want to go with? Let's go with a 1.5 inch NPT thread. And maybe the first thing that I really want to do is get into my equation editor and define all of my variables. What I care about is actual pipe size, actual, and of course a 1.5 inch pipe has an actual OD of 1.9. And then, and again, if you have any questions, just reference the chart for whatever size of pipe that you want to make. We care about TPI, and that's going to be 11.5. Let's care about pitch diameter at start. And of course, on the chart, the pitch diameter at start is going to be 1.79609. And then we care about maybe thread length. And that might look like maximum thread engagement. So I'm going to say thread length. And maximum thread engagement, I think it's just shy of 3/4 of an inch for an 1.5 inch pipe. So I'm going to make it a bit bigger, of course, 0.8, and apply that. So let's say that this is the things that we care about. I'm going to create a bunch of checks. Now for TPI, I may also want my pitch. So if I go to add pitch, which is 1 divided by TPI, you'll notice that we have red text, right? There's something wrong. And the reason is that TPI has an inch value on it, and a distance type expects an inch output, not a 1/inch unit. So we just need to create a different variable that will keep our unit straight. So I'm going to say just a generic, generic distance variable, and I'm going to make that value 1. So I'm going to make my TPI, or not TPI rather, but pitch. I'm going to say, and I'm going to open a parenthesis, 1 divided by TPI, and of course we have an error. So we're going to multiply that by distance variable, and we're going to square that. So 1 divided by an inch times inches squared gives us a single inch output, and then there's no error. So we just worked out our units, and that works. So we're going to say OK to that. Now getting back into my sketch, I can use my variables. I care about this being my nominal pipe size, or not my nominal, my actual pipe size. So I can select that. Now we are going just to the center line, so we're going to divide that by 2. And then I care about my taper, of course. Now taper in NPT is given by arctangent of 1/16. And if you look at this, you'll say, well, the arctangent of that angle is actually given between both sides, and we're doing only one side. So once again, we're going to divide that by 2, and that's should be the right taper. We care about thread length, of course. So I'm going to give that a horizontal dimension, and we can choose our thread length. And you can see that some of this is getting defined already. Now this can be just arbitrary. I'm going to make this whatever I want. I'll go 0.25. I can make this whatever I want. Right? If I'm making an adapter or something, you know, I may want to have some other NPT threads over here, some kind of fitting, and so, you know, I'll make this whatever dimension I want as well, and again this one as well. It might be standard to put a fillet on there, I'm not sure, but 50 thou is probably a pretty good size. So I'll say 0.05 and apply that. So we have a fully defined sketch, all the detail that we want. We're going to just revolve that, right? And I can choose my axis right there. So I have this tapered section that I can now put my threads on. We'll choose the XY plane, and I'll go ahead and save this right now. And now on my XY plane, I can create a trapezoid that I can start to sweep this with, right? So we're going to say horizontal here. We're going to say equal between these lines. And then I want to pull out the midpoint because our pitch diameter is going to be the midpoint of this imaginary triangle. So we'll say that we're collinear there. I'll grab a coincident and make sure that this line touches the very end of my construction line there. And then if you're in Pro and Expert, just put a point down. If you're in Atom, just use the point off of a construction line. And we'll make a midline constraint and make our point just in the middle, right? Makes a nice little marker of that. Now, the horizontal distance of this should be pitch divided by 8. And you can see that resizes pretty substantially. And then there's our midline, right? So we're going to grab a distance and make sure that these are 60 degrees apart, right? That would be our flank angle, or a thread angle, one of those terms. And now this, of course, is going to be our pitch diameter. And if we go to the chart, we can find our pitch diameter, but I think I've actually got it in a variable. So we'll hit this. We're going to say sort our favorites, and our pitch diameter is right there. We're going to divide that by 2. So our pitch diameter at start divided by 2. I think our only degree of freedom, we've got a few degrees of freedom. Thread height, we want to make sure that this is the correct height on our thread. So I'm going to grab a dimension here and say the distance from the top to the bottom, or the crest to the root, is going to be square root of 3. So we're going to say 3 to the power of 1/2. We're going to divide that value by 2. And then there's going to be some truncation, right? We have divided by 8 on the top and bottom. So we're going to say times 3/4 times our pitch. and that gives us our nominal thread height. And then I can say coincident. That edge is going to be coincident on that point, just so that it gives it a spot to live and be defined. So the very, very start of our thread profile is on that edge. That's fully defined, so we can get out of that. And then we'll make a subtractive helix. Our subtractive helix is going to go around our axis, right? That little reference line right there. And we're going to define our taper. That's going to be an angle, of course. And again, a tan of 1/32. And when I give this the pitch, again, our pitch is pitch. Right, when this calculates, and I'll give this thread height, or thread length, I think I made it. There you go. With the correct thread length, it works out, of course. We can see that we have the same crest size, or the crest length, on every iteration, on every thread. If I were to make this, say, a 16th, we can see that our crest width gets thicker every time, which means that we wouldn't have the same angle. So that's something to look for when we do our taper. Make sure that we have that kind of consistency. So again, this is all variable driven. And again, I'm going to just check my sketch here, and I do have the variable there. So yep, I think I've made this correctly so that this can update. Now this ends quite abruptly. It doesn't look that realistic, so maybe we want to add a runout or something like that. So I can start a sketch on my abrupt ending. We'll project to our sketch with maintained association, and we'll add another subtractive helix. Our axis will be, of course, our center axis. Our pitch will be our pitch, of course. I'll make something really small for our height. We don't need that much. So I'll say maybe 0.125. And then our taper needs a little bit of work. So we're going to say again, well, actually not our normal taper angle, but we'll do something large like 45 degrees. And there we have a runout that I don't believe cuts anything that we don't want cut. And we have a nice gradual runout that I think looks a lot more realistic for a thread like this. So nice simple runout if you'd like to add that. And so that should be our external NPT thread. Now we should be able to just open up our equation editor. And if I look at my chart, maybe I want a different size thread. Maybe I'll do a size for 2 inches. And for that, 2.375 would be our actual size. Our pitch diameter at start should be 2.26902. Our thread length is, maybe I'll make that a bit bigger, 0.85, and our threads per inch is still going to be 11.5. So all I should have to do is say OK, and we update to a new size. Now I may want to make this something a little bit more like, oh, I don't know, an internal thread. Well, this can be easily done, and we don't necessarily need to boolean or make a whole new thread, because the nominal thread, when you're nominal, the internal thread shares the same profile. And you could probably get away with nominal just by virtue of the taper anyway. So let's go and make this nominal. One of my favorite tricks is to use surfacing. So I'll create a sketch on the end of my thread. I'll make a circle and make it whatever length I think is best. And then I'm actually going to convert my model to a surface. So we're going to say convert solid to surface. Again, this is pro or expert license things. And then we're going to extrude that over our threads. I'm not being too particularly precise. I'm just going to cover my threads. Yeah, so that's probably good, right? So we're going to say OK. And now I can use my surface and I can trim my model. And again, I can hit reverse and see that the arrows are pointing outward. We want to trim everything inside of the surface. And then I can hide my surface. And that would be the most efficient thing to do. So we'll go down to surfaces here and choose hide. And there I have a complementary thread. I might need to do something about that runout, but I think, yeah, that runout kind of looks funny, but I guess it's a way to terminate it. And then yes, I can also delete face if I want my surface to be really removed. This is an extra step that is completely not necessary. In fact, let me show this. And now I can access my faces. So if I really want to get rid of it, right, the benefit to going and deleting every face is that if I have a workflow that has 8 different surfaces and you don't want to get them all confused, then you can get rid of surfaces as they're done so that you can just run through your tree and you can see the surfaces when they're showing, and then when they go away, when you're all done, you can keep your surfaces a little bit more straight. So I'm one to delete face on surfaces, but it's a lot of extra processing that isn't necessary, and you can rightfully just hide your surface to save a lot of things. Okay. So that would be an example of converting between the two. The runout may not be what you're looking for there, but so you can create these, and then you can just, again, go through your equation editor and update your numbers as you need, and it builds the thread for you. This is kind of getting into a video that Ex Machina made, and so I'd like to add the URL to that video as well. But we can use booleans, so if I start a new part, and in this part, right, maybe I extrude something that I want an NPT thread on. If I need to put an NPT thread here, I can say boolean subtract. I can say boolean unite too. I can choose which thread that I would like, and I can constrain this in the way that I want to. And just like that, we were able to make a subtraction and have some kind of thread in there. Again, you can be a bit more judicious than I was about how this thread was made, but that's an example of how you can, and how Ex Machina shows you can, create these kinds of things. So Ex Machina's video is very helpful. Check out that channel, give him a subscribe. He does some great content and great out-of-the-box thinking on making cool features with Alibre. And we're grateful for Ex Machina, Weekday Weekend, IQ Workshop, and a bunch of other channels that have done things with Alibre. So hopefully this is helpful in ways that you can use modeled NPT pipe threads in your work. Thank you for watching. If this is helpful, please subscribe to the Alibre channel, and we'll see you in the next one.